Tonight, we're going to explore one of the most profound questions in the future of human civilization. It is a question that sits behind every serious plan to send people to Mars, and it has very little to do with rockets, fuel, or the red landscape waiting at the other end of the journey. It has to do with whether the people we send are ever coming back. Not because the mission fails, not because something goes wrong out there, because coming back was never part of the plan. The first humans we send to Mars are being sent to stay, to live there, to die there, and the reason is hidden inside a number. The moon is roughly 384,000 kilometers away. Apollo astronauts made the round trip in roughly a week, with a communication delay of about 1.5 seconds. Mars sits, on average, 225 million kilometers from Earth, with launch windows opening only once every 26 months, and a one-way transit of 6 to 9 months. At the farthest point in its orbit, a signal home takes 20 minutes to arrive. And once you sit with those numbers long enough, a different question begins to surface. One that the engineers building these missions already know the answer to, but rarely say out loud. Whether the first humans who walk on Mars are going there to visit, or whether they're going there to stay. By the end of tonight, you're going to understand why the engineering and economics of that 295 million kilometer gap may quietly turn exploration into permanent colonization. Why the first colonists might accept a one-way mission, why more than 200,000 people have already volunteered for exactly that trip, and what it means for humanity to become, for the first time, a species that lives on more than one world. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about every exploration mission in human history. Every single one. Magellan's crew departed in 1519 and completed the first circumnavigation of the globe in 1522, arriving back in Spain with 18 men from an original crew of roughly 270. Edmund Hillary stood on the summit of Everest in 1953 and then came back down. The Apollo astronauts left the lunar surface, docked with the command module, and splashed down in the Pacific Ocean roughly a week after launch. They had photographs, they had samples, they had stories, and they came home to tell them. This is the pattern. Not just a tradition, not just a preference. The return journey was always part of the plan. The mission was never considered complete until the crew was home. Every major human expedition in recorded history was built on this assumption. You go, you discover, and then you come back. Mars may break this pattern, not by accident, by design. That possibility reshapes everything we think we know about what it means to explore. But before we can understand what a one-way journey to Mars actually means, we have to understand the geometry that makes it so different from anything humanity has attempted before. Start with the moon. The moon sits 384,400 kilometers from Earth. That is roughly 238,900 miles. Apollo reached it in about 3 days. Total mission durations ran between 8 and 12 days. From the lunar surface, the astronauts could look up and see Earth hanging in the black sky, a blue and white marble, vivid and close and real. Psychologically and operationally, they were never far from home, and the numbers confirm that. A radio signal traveling at the speed of light takes about 1.5 seconds to cross the Earth-Moon gap. Ground controllers in Houston could hear a question, think about it, and respond before the astronaut had even finished waiting. Communication was effectively real-time. If something went wrong, mission control could talk a crew through the problem in something close to a normal conversation. Now take everything you just understood about the moon and set it aside. Because Mars is not the moon, just further. Mars sits, on average, 225 million kilometers from Earth, about 140 million miles. But that average conceals something important because Earth and Mars both orbit the Sun on their own independent schedules, and their relative positions are constantly changing. At the closest point in their orbits, called opposition, the two planets are separated by roughly 55 million kilometers, about 34 million miles. At the farthest, when they sit on opposite sides of the Sun, the gap stretches to approximately 400 million kilometers, about 248 million miles. Let me put that in perspective. The moon is roughly 384,000 kilometers away. At closest approach, Mars is about 143 times that distance. At farthest, it is more than 1,000 times the Earth-Moon gap. If the distance to the moon were a single step, the average distance to Mars would be a walk of several city blocks. The farthest separation would take you across a small country. But here's where it gets strange. Because the two planets are always moving, you cannot simply point a rocket at Mars and fire. You have to aim at where Mars will be by the time your spacecraft arrives, which takes 6 to 9 months, depending on the trajectory you choose. And the geometry for a favorable launch only lines up roughly every 26 months. Miss a launch window, and you do not wait a few weeks. You wait more than 2 years for the orbital mechanics to come back around. The schedule is not set by engineers or budgets, it is set by physics, and the communication delay does not stay fixed while you wait. At closest approach, a radio signal takes about 3 minutes to cross from Earth to Mars. 3 minutes there, 3 minutes back. So the minimum round-trip communication time is 6 minutes. That is already long enough to make a normal conversation feel strange and halting. At greater separations, the delay stretches to 20 minutes one way, 40 minutes or more for a round trip. Think about what that means in practice. An astronaut on Mars notices something alarming. They send a message to Earth. Mission Control receives it 20 minutes later, formulates a response, and sends it back. The astronaut gets the reply 40 minutes after they first asked. Whatever crisis prompted the question has already resolved itself, one way or another, long before any advice from Earth could possibly arrive. The letter versus phone call comparison is the honest one. This is not a conversation with a delay. It is correspondence, sent and then waited on. And during the 6 to 9 month crossing between the two planets, the crew is not just far from Earth in kilometers. They are far from Earth in time. Every decision they face, every emergency they encounter, every system failure or medical problem that arises, they face alone. Not with a slight delay in guidance. Completely alone. The moon always had a lifeline. The crew of Apollo 13 lost power and oxygen in April 1970 and made it home in 4 days because the distance allowed it. A Mars crew in trouble has no equivalent rescue. No retrieval mission can be organized and launched in 40 minutes. No engineer in Houston can walk a crew through a repair in real time. The 225 million kilometer average is not just a larger number than the moon's 384,000 kilometers. It is a categorically different kind of mission. Not a greater distance, a different world entirely. The geometry does something else too. It transforms what the word rescue even means. It transforms what the word emergency means. It transforms the relationship between the crew and the institution sending them. And as we will see, it begins to transform the mission itself, from a trip to a destination. That change in the nature of the mission is where the real story begins. That change in the nature of the mission begins the moment they arrive. After 6 to 9 months of crossing empty space, the spacecraft does not simply glide down to the surface. It breaks into Mars orbit first, slowing itself against the planet's gravity, circling above a rust-colored world that looks deceptively calm from altitude. The crew has survived the crossing. The hard part, most people assume, is over. It is not over. The hardest 7 minutes of the entire mission are still ahead. To understand why, you need to understand what Mars's atmosphere actually is. Earth's atmosphere is dense enough to do useful work. A parachute deployed above Earth can slow a capsule gently enough that the ground impact is survivable. The physics works. But Mars's atmosphere is roughly 1% the density of Earth's. 1%. A parachute that would safely lower a capsule to the ground on Earth becomes nearly useless here. The air is too thin to generate the drag you need. You fall too fast. But here is the problem. 1% is not zero. The atmosphere is thin, but it is not absent. And that small residual atmosphere is thick enough to generate something dangerous. When a spacecraft descends at orbital velocity, roughly 5 kilometers per second, the air in front of it cannot move out of the way fast enough. It compresses. It heats. The heat shield on the spacecraft's underside faces temperatures that would destroy exposed metal in seconds. Temperatures comparable to the surface of the sun. So the atmosphere is too thin to slow you down, but thick enough to try to burn you alive. Not too little, not too much, but wrong in a way that makes everything harder. This is the Goldilocks failure. The atmosphere sits precisely in the gap, where no single technology solves the problem. Heat shield alone gets you through the thermal phase, but leaves you plummeting at hundreds of meters per second. Parachute alone in that thin air bleeds off some speed, but nowhere near enough. Retro rockets alone, firing from the beginning of descent, would burn through fuel reserves in minutes before you reach the surface. The only solution is all three, in sequence, precisely timed. The sequence goes roughly like this. The heat shield absorbs the thermal phase, then the parachute deploys, pulling the spacecraft back from terminal velocity while the heat shield falls away. Then the retro rockets ignite, slowing the final approach and allowing a controlled landing. Each phase must hand off to the next at the right moment, the right altitude, the right speed. Too early on the parachute and it tears apart under aerodynamic loading. Too late, and there is not enough distance to slow down before impact. A retro rocket that fires at the wrong altitude does not give the spacecraft a second chance to correct. One attempt. No retries, no abort option that leaves the crew on the surface unharmed. And during all of it, Earth cannot help. This is the part that stops people when they first hear it clearly. The radio delay at Mars is somewhere between 3 minutes and 20 minutes one way, depending on where the planets are in their orbits. Even at the very closest approach, a signal from the spacecraft takes 3 minutes to reach Earth, and any response takes another 3 minutes to come back. 6 minutes, minimum. During a 7-minute landing sequence, Mission Control cannot receive a single report and send back even one response before the outcome is decided. They are watching a film that was already shot. By the time mission controllers in Houston see on their monitors that the spacecraft has entered the atmosphere, the landing has already happened. The crew is either alive on the surface or gone. The people who built the spacecraft, who designed every system, who trained for years to guide this mission, can do nothing except wait to find out. And automated systems make thousands of decisions in those 7 minutes. Sensors measure altitude, velocity, attitude. Computers calculate trajectories and trigger each phase of the sequence. The spacecraft navigates the most dangerous stretch of the mission entirely on its own, without a human hand anywhere in the loop. Think about what that means for the crew inside. They are inside a vehicle decelerating from orbital velocity, heat shield glowing, structural loads pressing through the frame, each phase of the sequence triggering automatically around them. They can monitor. They cannot intervene in any meaningful way. They have trained for every contingency, but many contingencies have no survivable resolution. They ride it out. NASA calls this the 7 minutes of terror. That phrase is not rhetorical. It is an accurate description of the interval between atmospheric entry and surface touchdown, during which nothing and no one can change the outcome. There is something worth sitting with in that number. 7 minutes. After 6 to 9 months of travel, after a crossing of hundreds of millions of kilometers, after all the preparation and training and engineering, the moment that decides everything lasts 7 minutes. And in those 7 minutes, the crew is more alone than they have been at any point in the journey. If the sequence completes successfully, the retro rockets cut out and the surface is there. Rust-colored sky, rocky desert stretching to a horizon that sits lower than any horizon on Earth, because Mars is smaller and the curvature falls away faster. Distant mountains catching the last light. The light itself is strange, filtered through fine dust suspended in that thin atmosphere, giving the air a quality that has no equivalent on Earth. There is something almost familiar in it, and something profoundly foreign at the same time. The crew has arrived. They are the first humans to stand on another planet, and they already know, from the moment they touch down, that the planet they are standing on has no intention of making any of this easy. They are standing on Mars now. That fact alone is extraordinary, but the crew knew, even in the moment of arrival, what the next question would be. Not how to survive on the surface, not how to begin the work. The question that was already there, present from the instant the retro rockets cut out, was simpler and more final than either of those. How do they leave? Think about what it takes to leave a planet. Any planet. You need thrust. Thrust requires fuel, and fuel in the quantities a rocket requires is heavy, almost unimaginably heavy. The Saturn V is the most instructive example we have. When it stood fully loaded on its launch pad at Kennedy Space Center, it weighed approximately 2,800 metric tons. That is roughly 6.1 million pounds. Of that total mass, approximately 2,600 metric tons was fuel. Just fuel. The command and service module, the part that actually went to the moon and came back, weighed roughly 43 metric tons. That is about 1.5% of the rocket's total mass. The rest, the towering structure, the 5 massive engines, the fuel lines and tanks, everything below the tiny capsule at the tip, existed solely to carry those 43 metric tons off the Earth and into space. The Saturn V was approximately 93% fuel by weight. Just to reach the moon, a body with 1/6 of Earth's gravity and no atmosphere at all. Now think about Mars. Mars is not the moon. Its gravity is 38% of Earth's. That is stronger than the moon's by a significant margin. It also has an atmosphere, thin as it is, and that atmosphere creates drag during ascent, working against any vehicle trying to climb. A Mars ascent vehicle capable of returning a crew of 4 or 5 people, plus the equipment they need to survive the return journey, has to be comparable in scale to a major Earth launcher. And it will be, like every rocket ever built, almost entirely fuel. Here is where the mass spiral begins. And once you see it, you cannot unsee it. If you want to launch a rocket off Mars, you need fuel. A lot of it. You could, in theory, bring that fuel from Earth. You load the fuel onto a spacecraft, fly it across space, enter Mars orbit, and land it on the surface. But landing something on Mars requires its own fuel for deceleration and controlled descent. The heavier the thing you are landing, the more landing fuel you need. And landing fuel is itself mass, which means the spacecraft you are landing is heavier, which means you need even more landing fuel. The spiral turns on itself. A fully fueled ascent stage would be enormously heavy. Landing something that heavy on Mars would require a quantity of landing fuel that itself approaches the mass of the thing you are trying to land. That additional fuel also has to be transported from Earth, which means launching it from Earth, which requires fuel for that launch. The numbers collapse. Every kilogram of return fuel you try to bring from Earth multiplies into many more kilograms that have to be launched, transported, and landed before the first kilogram can be used. The mass budget does not close. It is a snake eating its own tail, each bite requiring a larger bite behind it, with no stable endpoint. This is not a solvable engineering problem in the way that most engineering problems are solvable. It is not a matter of building a bigger rocket or writing a larger check. The physics are unforgiving. Bringing preloaded return fuel from Earth is, for a crewed Mars mission of any practical scale, not possible. Wait. This is the conclusion that changes everything about how a Mars mission has to be designed. The proposed solution is a concept called in situ resource utilization. In plain terms, you do not bring the return fuel from Earth, you make it on Mars. The Martian atmosphere is thin, but it is mostly carbon dioxide. The Martian soil likely contains water ice in accessible locations. Through a series of chemical reactions, it is theoretically possible to extract hydrogen and carbon from those local sources and synthesize rocket propellant directly on the surface. A fuel production plant, landed on Mars before the crew arrives, runs for months or years, slowly filling a tank. By the time the crew lands, the return fuel is already there, waiting. That is the plan. It is elegant in principle. It is extraordinarily demanding in practice. The plant has to work perfectly, in a place no one has ever been, with no one available to repair it if something fails, for however long it takes to fill the tank. But the deeper point is this: landing on Mars is hard. The 7 minutes that came before were among the most dangerous moments in human spaceflight history. And yet, in a certain sense, landing is the simpler half of the problem. The harder half was always return. Every kilogram the crew wants to take off the surface of Mars either had to be manufactured there from local materials, or landed there at a mass cost so severe it approaches the impossible. The planet will not simply let them leave. The physics of departure are in their way, more demanding than the physics of arrival. The crew is on the surface now, and the fuel tank is either full or it is not. If it is not full, they stay. And the question of what happens if the fuel plant fails, if the chemistry does not work, if the tank is only half full when the launch window arrives, is not an abstract concern. It is the question that has always lived at the center of this mission design. The hard part was never getting there. So what does it actually take to make rocket fuel from a planet's breath? The answer begins with something Mars has in extraordinary abundance. The Martian atmosphere is 95.3% carbon dioxide. Not a trace amount, not a useful fraction. Almost everything up there is carbon dioxide, compressed thin across a cold and silent sky. That single fact is what makes the whole plan possible. The first step is to pull that atmosphere in, compress it, and purify it. A mechanical pump draws Martian air into a processing unit, stripping away the small fractions of nitrogen and argon until what remains is nearly pure carbon dioxide ready to feed a reactor. The equipment is not exotic. Industrial chemistry has worked with compressed carbon dioxide for well over a century. What makes this different is the location. The second ingredient is water. Mars has it, but not in any form you can simply collect from a stream. Water ice sits locked in the soil, particularly at high latitudes, and in permanently shadowed polar craters where sunlight never reaches. One way to extract it is to heat the soil gently, driving sublimation, turning the buried ice directly into vapor that can be captured and condensed. Another is to drill and draw the vapor up through sealed tubes. Either way, the yield is slow and the machinery must operate in conditions that would destroy most unprotected electronics within weeks. But it works. The ice is there. The question is only one of engineering patience. Once you have water, you split it. Electrolysis runs an electrical current through the liquid and breaks it apart at the molecular level. 2 molecules of water become 2 molecules of hydrogen gas and 1 molecule of oxygen gas. The oxygen can be stored directly. It is one of the 2 propellants you need. The hydrogen becomes the other half of the feedstock for the next step. This is where a discovery made in 1897 becomes central to a Mars mission more than a century later. A French chemist named Paul Sabatier found that combining carbon dioxide and hydrogen over a nickel catalyst at moderate temperatures produces methane and water. The reaction runs like this. 1 molecule of carbon dioxide combines with 4 molecules of hydrogen to yield 1 molecule of methane and 2 molecules of water. The Sabatier reaction, as it is now called, is exothermic. It releases heat as it runs. That heat can be used to help drive the process, reducing the energy you need to pump in from outside. The reaction is well understood. It has been run in Earth laboratories thousands of times. It is not new science. But here is where it gets strange. The water that comes out of the Sabatier reaction is fed directly back into the electrolysis unit, which produces more hydrogen, which feeds back into Sabatier, which produces more water, which feeds back into electrolysis. The system becomes a loop, a closed cycle where the water is used, regenerated, and used again. Think of it as a kind of chemistry still, continuously redistilling its own outputs, where the only thing the system continuously consumes from outside is more carbon dioxide drawn from the atmosphere above. You feed it Martian air, you draw off methane and oxygen from the other end. The carbon and the hydrogen cycle through the machinery in an endless handoff, each product becoming the next input. Not a partial loop, not a system that occasionally recycles. A true closed cycle where only the atmospheric feedstock needs continuous replenishment. The methane and oxygen that come out of this process are real rocket propellants. Methane burns cleanly and energetically. Oxygen is the oxidizer that makes combustion possible in the vacuum of space, where there is no atmospheric oxygen to draw on. Together, they can power a rocket off the Martian surface and back toward Earth. The chemistry is solved, but the products must then be stored for months or years before a crew arrives to use them. This is where a different kind of problem begins. Liquid methane must be held at negative 161 degrees Celsius to stay liquid. Liquid oxygen must be held at negative 183 degrees Celsius. Both temperatures are colder than anything Mars naturally produces. The coldest recorded temperatures on the Martian surface hover around negative 140 degrees Celsius at the poles in deep winter. That is not cold enough. Active refrigeration is required to keep the propellant from boiling away. And even with refrigeration, even with insulation layered around every storage tank, some boil-off happens. It is unavoidable. Cryogenic liquids are always pressing against the boundary between liquid and gas, always finding the tiniest path toward evaporation. Over 18 months, over 24 months, the losses accumulate. This matters because the fuel plant will be running and storing propellant long before any crew arrives. The tank must be full, or close enough to full, by the time the launch window opens. Any propellant lost to boil off is propellant that has to be overproduced from the start, which takes more time, more power, more margin built into a system that is already stretched. And the power demand is not small. A fuel production plant generating 30 to 50 metric tons of propellant over 18 to 24 months may need somewhere between 100 and 200 kilowatts of continuous electrical power. Not peak power during a sprint. Continuous power, day and night, for nearly 2 years. 100 to 200 kilowatts is roughly the draw of 70 to 140 average American homes running simultaneously, without interruption. Think about that for a moment. A small neighborhood's worth of electrical demand, sustained on the surface of another planet, in a place where no power grid exists, and no repair crew can arrive if something fails, for the better part of 2 years. The chemistry is elegant. The loop is clean. The reaction that Paul Sabatier described in a Paris laboratory in 1897 does exactly what the mission needs it to do. But the system that runs that reaction, and cools the products, and holds them against the slow pressure of evaporation, and does all of this autonomously and reliably for months before anyone arrives to check on it, demands power on a scale that cannot come from solar panels alone in the dimmer light at Martian distances from the sun. The question of where that power comes from is not a footnote to the fuel problem. It is the next problem entirely. Let's stay with that number for a moment. 100 kilowatts, continuous, on a planet that has never generated a single watt for anyone. That is what the fuel plant needs. Not occasionally, not during peak operating hours, not during the Martian day when conditions are favorable. Continuously, night and day, through every season, through every storm. The chemistry will not wait for the sun to come back out. The refrigeration that holds liquid methane at negative 161 degrees will not pause. The compressors drawing carbon dioxide from the atmosphere will not cycle down because conditions are difficult. The system runs, or the mission ends. So the question becomes unavoidable. Where does the power come from? The most obvious answer is solar. Mars receives sunlight. Panels produce electricity. But here is where the numbers begin to close in. At Earth's distance from the sun, sunlight arrives with an intensity of about 1,368 watts per square meter. That is the baseline. At Mars, the average is roughly 590 watts per square meter, less than half. And that figure is local noon, clear sky, equator, panels aimed perfectly at the sun. It is the best case. Reality shaves it down further from there. The Martian day is only slightly longer than Earth's, which means half of every rotation the panels generate nothing at all. Seasons tilt the planet, reducing solar angle. The atmosphere, thin as it is, still carries dust, and dust scatters light. And dust on the panels themselves, accumulating gradually over months, reduces output further still. Factor all of that together, and a solar-only fuel plant producing 100 kilowatts of continuous power would need several thousand square meters of panels. That is a lot of hardware to land on Mars, a lot of connections to make, a lot of surface to keep clean, a lot of individual components that can fail. Not a neat solution. An enormous one. But the size is not even the core problem. The core problem is named dust. Dust on Mars is not an occasional inconvenience, it is a seasonal force. Every Martian year, the planet enters a period of elevated dust activity. Winds pick fine particles off the surface and carry them into the atmosphere, reducing the sunlight that reaches the ground. In moderate storms, the the reduction can reach 50%. In major storms, it can reach 99%. The sky does not merely dim. For weeks, sometimes months, it becomes almost opaque. Global dust storms, the kind that envelope the entire planet simultaneously, occur roughly every 3 to 4 Martian years. They are not rare. They are predictable. They will come. In 2018, a global dust storm arrived on Mars and did not leave. It stretched for months. The sky turned dark, and a small rover named Opportunity, which had been operating on the Martian surface for nearly 15 years, quietly ran out of power. Opportunity was solar-powered. When the storm thickened, the panels could no longer charge the batteries enough to run the heaters that kept the rover's electronics from freezing. Mission controllers sent signal after signal. The rover did not respond. It was never heard from again. It is still there now, somewhere on the floor of Perseverance Valley, covered in dust, silent. A solar-only fuel plant would share Opportunity's vulnerability. Not the same rover, not a small research machine. The entire return fuel production system. The one thing standing between the crew and a one-way trip. That is not a risk engineers can accept. So attention turns to nuclear power. And here the picture shifts. Nuclear reactors produce power continuously, independent of sunlight, independent of dust storms, independent of day and night cycles. The fuel is not the sky. The fuel is uranium. You bring it with you and it generates heat, and that heat drives electricity, and it does not care what the Martian atmosphere is doing. NASA has been developing a reactor called kilometer. It is a uranium fission system, compact, reliable, producing about 10 kilowatts of continuous power. It is roughly the size of a trash can. 10 kilowatts is useful, but the fuel plant needs 100 or more. So the math moves in one of the two directions. Either you land 10 to 20 kilopower units, operating in parallel, each one contributing its share to the total, or you develop a single larger reactor, something capable of producing 100 kilowatts or more, and land that instead. Both paths are technically plausible. The Soviet Union ran nuclear reactors on remote Arctic bases for decades, supplying power to stations where no grid reached and no repair crew could arrive quickly. The concept is not new, but nuclear on Mars is not simply a matter of building the reactor. It begins long before Mars, on a launch pad on Earth. Launching nuclear material from Earth raises concerns that solar panels do not. A rocket carrying a live reactor, or even enriched uranium destined for assembly, carries a different kind of risk on the way up. Launch failures happen. If a rocket breaks apart during ascent, and radioactive material scatters over a populated area, or falls back into the ocean in a way that cannot be fully recovered, the consequences reach far beyond the mission. These concerns are manageable. Launch profiles can be designed to minimize exposure. Reactors can be kept subcritical until they are safely in space, or on the Martian surface. But the political dimension is real, and the engineering constraints that come with it add complexity that solar panels simply do not carry. Then, there is the question of cooling. A nuclear reactor generates heat as a byproduct of the fission process. On Earth, cooling a reactor means water. Water absorbs heat efficiently, carries it away, dissipates it through cooling towers. On Mars, water cooling is not available. Water is scarce and mostly frozen, and using it to cool a reactor would consume one of the most precious resources on the planet. Instead, the reactor must shed its waste heat by radiation. Large panels, not solar panels but thermal radiators, extend from the reactor and glow with heat, slowly releasing energy into the thin Martian air. Think of it as a thermos working in reverse. A thermos keeps heat in by minimizing contact with the outside. These radiators must push heat out into an environment that does not accept it particularly well. The thin atmosphere carries almost no heat by convection. The ground conducts slowly, so the radiators must be large enough to shed the required heat through infrared radiation alone, and they must do it reliably, in cold that can reach well below -100 degrees, without cracking, without failing, without anyone to replace them. More surface area, more mass brought from Earth, more connections that must survive landing. more components that must function without maintenance. Whatever path the mission chooses, solar or nuclear or some combination of both, the system faces the same final requirement. It must work by itself for months, possibly for more than a year before any human foot touches Martian soil. That means sensors watching temperature, pressure, flow rates, and power output. It means control software making thousands of small decisions every day, adjusting reactor output, routing power between systems, diverting to batteries when demand exceeds supply. It means some capacity for physical intervention when components degrade or fail, whether from small maintenance robots or from redundant systems designed to take over automatically. It means dust clearing mechanisms for any solar components in the array, because dust will accumulate regardless of season. The environment the system operates in is not gentle. Radiation from the sun is higher on Mars than on Earth, because Mars has no magnetosphere to deflect charged particles. Temperature swings between Martian day and night can exceed 60 degrees. The dust is chemically reactive, fine enough to work into seals and bearings, abrasive enough to degrade surfaces over time. This is what the power problem looks like when you open it fully. The fuel chemistry is the easy part. Paul Sabatier worked that out in 1897. The Sabatier reaction runs reliably. Electrolysis splits water cleanly. Methane and oxygen emerge from the process exactly as physics predicts. On that level, everything works. What is hard is generating, on another planet, enough electricity to run that chemistry continuously without anyone present to restart a failed system, repair a broken radiator, brush dust off a panel, or make a judgment call when something behaves unexpectedly. And the power problem is not the last one. So stay with that machinery a moment longer. Not the chemistry, not the power source, not the question of solar panels versus reactors. The machinery itself. What happens to it while it waits? The fuel plant arrives on Mars and begins working. That is the plan. It runs autonomously, as we covered, making thousands of small decisions without anyone present to guide it. But there is a layer beneath the autonomy problem that is easy to overlook. The environment is not simply demanding in the way that a harsh climate is demanding on Earth. It is continuously destructive in ways that compound across months and then years. The production target is large. A Mars ascent vehicle needs somewhere between 30 and 50 metric tons of propellant to lift the crew off the surface and reach orbit. 50 metric tons is 50,000 kilograms. Think of it this way. An average automobile weighs roughly 1,400 kilograms. 50 metric tons is approximately 35 of those automobiles, every kilogram of it manufactured from Martian resources by equipment that arrived from Earth. A well-designed system might produce between 100 and 200 kilograms of propellant per day. At that rate, filling the tank to the minimum required level takes somewhere between 9 and 18 months of continuous, uninterrupted operation. And here is what those 9 to 18 months look like from the outside. Mission planners on Earth watch a telemetry feed. Numbers come back across the delay. The tank fills, slowly, day by day. A pump runs at slightly reduced efficiency. A sensor drifts. A dust storm approaches. They watch. They send commands that arrive 20 minutes later. They receive responses 20 minutes after that. Any breakdown, a pump failure, a reactor going offline, a storm that pushes the system past its designed operating limits extends the timeline. Weeks become months. The launch window approaches. The tank is not full, but something was wrong. The breakdown that causes the most damage might not be dramatic. It might not be a sudden failure at all. Mars does this to equipment slowly. Near the equator, on a summer day, surface temperatures can reach 20 degrees Celsius. That is a mild afternoon by Earth standards. Then the sun sets. By midnight, the same location has dropped to minus 73 degrees Celsius. That is a swing of nearly 100 degrees in a matter of hours, and it happens every single Martian day. At higher latitudes, or in winter, the lows fall further. Minus 125 degrees Celsius. The thermal cycling range across a full Martian year exceeds 200 degrees. Most materials do not survive that indefinitely. Seals crack. Lubricants that flow at room temperature become thick and resistant at minus 70, and essentially solid at minus 125. Batteries lose capacity as temperatures fall because the chemical reactions that produce current slow down. Electronics that were calibrated at one temperature behave differently at another. Accumulate small errors. Drift. None of these effects are catastrophic on their own. That is the problem. Think of bending a paperclip. Once it holds, twice it holds, 10 times it holds. But something is happening inside the metal each time. The crystal structure is deforming. Stress fractures are forming at the bend point, too small to see. On the 30th or 40th bend, the clip snaps. The failure looks sudden. It is not sudden. It was accumulating across every cycle, building invisibly toward the threshold. Mars thermal cycling works the same way. A seal that survives the first 100 temperature swings may fail on the 200th. A bearing that performs within spec for the first 6 months may begin to stick in month 9. The equipment is not aging in the sense of wearing out from use. It is aging in the sense of cycling through mechanical stress every single day toward a point of failure that is difficult to predict and impossible to stop. The radiation compounds this. Mars has no magnetosphere, as we covered. Cosmic rays and solar radiation reach the surface continuously. Over time, radiation does specific things to materials. It flips individual bits in computer memory, random errors that accumulate in logic systems. It degrades solar panel efficiency by damaging the semiconductor layers inside each cell. It embrittles plastics and composites, the same way sunlight eventually makes plastic garden furniture brittle and prone to cracking. A fuel plant that has been operating on the Martian surface for 2 years before the crew arrives has absorbed a significant cumulative radiation dose, not a catastrophic dose, significant, measurable, affecting performance at the margins in ways that may not trigger any individual alarm, but that add up. The standard engineering answer to all of this is redundancy. Build in backups. 2 reactors instead of 1. Multiple pumps on the same line. Backup sensors watching the primary sensors. Controllers that can take over if a primary controller fails. Design the system for graceful degradation so that it keeps functioning even as individual components fail, operating at reduced capacity rather than stopping entirely. This is the right answer. It is also not a free answer. Redundancy compounds complexity. More components means more connections. More connections means more failure points. A system with 2 reactors, 3 pump arrays, backup controllers, and redundant sensor networks is not twice as complex as a system with 1 of each. It is more complex by an order of magnitude, because every interface between redundant systems is itself a potential failure point. The more elaborate the backup architecture, the more elaborate the set of ways it can fail. Engineering reliability is not simply a matter of adding backups until the problem goes away. And then there is the testing problem. Building the hardware on Earth is possible. Testing it thoroughly on Earth is not really. Earth test chambers can reproduce cold temperatures. They can reproduce low pressure. They can reproduce radiation exposure over compressed time periods. What they cannot fully reproduce is the Martian dust. It is finer than most terrestrial dust, with a composition and abrasiveness that no chamber test has completely replicated. The gravity is different. The atmospheric composition introduces chemical interactions that are difficult to model in a test environment. The combination of all these factors simultaneously, sustained over 18 months of continuous operation, is not something any facility on Earth can reproduce. Some lessons can only be learned by operating actual equipment on the actual surface of Mars. The first generation of Mars hardware will be, simultaneously, the first generation of its own field tests. Not proven technology deployed in a known environment. Technology whose real performance envelope can only be discovered in the place it was designed to operate, by which time the first crew may already be committed to the mission. The response to that uncertainty, again, is redundancy at the mission level. Send not 1 fuel plant, but 3 on separate cargo missions, landing in different locations, all running in parallel, and building toward a combined reserve far beyond the minimum required. Start production years before the crew launches. Stockpile. But every additional cargo mission costs hundreds of millions of dollars. the cost arithmetic closes quickly. A mission architecture built around a single fuel plant might carry a total price of around $50 billion. 3 fuel plants in parallel, with the additional cargo missions, the additional monitoring, the additional redundancy in the propellant stockpile, pushes that figure towards $70 or $80 billion. And those figures assume nothing unexpected happens along the way. This is where the question becomes less about engineering and more about what a society is actually willing to fund. A round-trip mission architecture requires all of this to work. Every piece of it, across years, in an environment we cannot fully replicate, using hardware we have never operated there before. A one-way mission does not require a working return fuel plant at all. It does not require 50 metric tons of propellant to be sitting on the surface before anyone lands. The thermal cycling problem does not disappear for a one-way mission, but it changes in scope. The radiation problem is still real, but it applies to different systems. The cost spiral that emerges specifically from the requirement to get people off the surface and back to Earth is, by definition, absent. This is not a small difference. It is the structural argument that has been building since the first cargo mission was planned. Every engineering challenge traced in the past several sections arrives at the same pressure point. The environment is harder than Earth testing can replicate. The redundancy required for confidence drives costs upward toward a number that may exceed what any single program can sustain. And the mission designers working through these numbers in detail are the same ones quietly asking whether the round-trip requirement is the source of the problem, rather than just a feature of it. That question has not been answered yet, but the hardware problem is not the last thing pushing it forward. To understand where Mars sits on the cost curve, you need to understand where Apollo sits first. That is the only honest comparison we have. The only time humanity built a program large enough, expensive enough, and technically demanding enough to serve as a real reference point. So pull back from the engineering details for a moment. Pull back from the fuel plants and the thermal cycling and the redundancy arithmetic, and look at the one precedent that contains all of it. Apollo cost $25.8 billion. That was 1960 to 1973 money. Adjust for inflation, and that figure becomes approximately $280 billion in today's terms. $280 billion, spent over roughly 13 years across one of the most concentrated mobilizations of engineering talent in human history. What did that buy? 12 people landed on the moon. 6 missions reached the surface. Total time spent on the lunar surface across all 6 missions was approximately 9 days. 9 days combined. The longest single mission from launch to splashdown lasted about 12.5 days. That was the outer limit. After that, the crew came home. At the program's peak in 1966, more than 400,000 people were working on Apollo, directly or indirectly. Engineers, machinists, technicians, contractors, subcontractors, support staff, spread across the country. NASA's share of the United States federal budget at that peak exceeded 4%. Today, NASA receives less than half of 1%. Apollo was not a line item. It was a national mobilization. And still the engineering was strained to its absolute limit. The Saturn V, which carried the missions to the moon, remains the most powerful rocket ever flown to completion. No rocket since has matched it. Building it required entirely new manufacturing facilities. The vehicle assembly building at Kennedy Space Center, constructed specifically for Apollo, remains among the largest buildings in the world measured by enclosed volume. Tracking stations had to be built on islands scattered across the Pacific and Atlantic just to maintain continuous communication with a capsule 3 days away. All of this was accomplished without modern computers, without modern software, without any established medical protocols for extended weightlessness, because none existed. Every life support system had to be near perfect from the first flight, because there was no room for iterative failure. Here is what that life support involved. Carbon dioxide had to be scrubbed from the cabin continuously using lithium hydroxide canisters. Physical chemical canisters, replaced on a schedule. The lunar surface itself ranged from positive 127 degrees Celsius in direct sunlight to negative 173 degrees in shadow. 300 degrees of thermal range across a few meters of ground. And then Apollo 13 happened. In April 1970, an oxygen tank in the service module exploded. The command module lost power. 3 astronauts retreated into the lunar module, the small 2-person vehicle designed to land on and lift off from the moon. It was designed to support 2 people for 2 days. They used it to support 3 people for 4 days. They improvised carbon dioxide scrubbers out of duct tape and plastic bags. They shut down nearly every system on board to conserve power. They endured temperatures that fell near freezing inside the spacecraft. They did the calculations by hand, and they survived. Apollo 13 established something important. It established that astronaut survival in extremis depends not on having the right equipment for every scenario, but on improvisation. On people who can solve a problem that no training manual anticipated, under time pressure, with whatever is in the room. That fact will matter later. For now, remember it. All of Apollo, every dollar, every person, every improvised solution was built for missions to a body 3 days away. The moon has no atmosphere. It has 1/6 of Earth's gravity. Communication delays between Earth and Moon were measured in seconds. Earth was always visible from the lunar surface, and if something went badly wrong, the astronauts could be back in Earth orbit within 3 days. Back in a hospital within 4. That is tight, but it is survivable. Now look at what a round-trip Mars mission actually requires. Not a longer version of Apollo. Not a scaled version. Something categorically different in almost every dimension simultaneously. The mission duration alone changes everything. Apollo missions lasted roughly 1 week. A Mars mission lasts approximately 3 years. That is not a multiplier of 2 or 3. It is a multiplier of more than 150. Every consumable that gets used over time, food, water, air, medicine, spare parts, extends by that factor. The crew cannot be 3 astronauts in a capsule the size of a van. A 3-year mission requires a crew of 6 to 8 people in a habitat large enough to sustain psychological health across that duration. Small rooms and narrow corridors are survivable for 12 days. They are not survivable for 3 years. Life support changes fundamentally in character. On Apollo, carbon dioxide scrubbing worked through stored lithium hydroxide canisters because the mission was short enough to carry sufficient supply. On Mars, you cannot carry enough of anything consumable for 3 years. Air and water must be recycled, not supplemented, not partially recovered. Recycled continuously through regenerative systems that have no Earth analog at the scale and duration required. A stored consumable approach to life support does not work for a mission measured in years. Power changes. Batteries and fuel cells, sufficient for Apollo, are not sufficient for 3 years on the Martian surface. The mission needs nuclear reactors or solar arrays large enough to power a small settlement, running continuously. And the vehicle architecture alone multiplies the mass. Apollo carried a single lunar module, about 15 metric tons. That vehicle descended to the surface, ascended back to the command module, and the mission was done. A Mars mission requires a descent vehicle, a surface habitat, surface rovers, an ascent vehicle capable of lifting crew off a planet with 38% of Earth's gravity, an in-situ resource utilization plant to produce propellant, and the infrastructure to tie all of it together. Not one vehicle, a surface program. Think about what that does to mass. The Apollo command and service module weighed roughly 32 metric tons. A fully loaded Mars transit vehicle, the spacecraft that carries the crew across space for 6 to 9 months each direction, would weigh several hundred metric tons. The lunar module at 15 metric tons was a remarkable feat of lightweight engineering. A Mars lander with a habitat capable of supporting 6 to 8 people for years would weigh over 100 metric tons. That is not an estimate. That is a flaw. Mass is not an abstract engineering parameter. Mass is cost. Every kilogram sent to Mars has to be accelerated out of Earth's gravity well, flown across interplanetary space, and decelerated into Mars orbit. More mass requires more launch fuel. More launch fuel requires bigger rockets. Bigger rockets are more expensive to develop and build. The costs multiply at every stage of the chain, not just once. Apollo cost $280 billion for 12 people, 9 days of surface time, 6 missions, to a body 3 days away, in missions that lasted under 2 weeks. Everything about that program was pushed to its engineering and budgetary limits. It consumed more than 4% of the federal budget for years. It required 400,000 people. It invented the protocols it needed because none existed. And even then, survival came down to duct tape and improvisation. A round-trip Mars program does not resemble Apollo, the way a longer road trip resembles a shorter one. It resembles something for which Apollo is the only available lower bound. A mission that is larger in mass, longer in duration, more complex in architecture, farther from Earth, and more dependent on systems that have never been built. Not a comparable undertaking, something fundamentally more expensive. And the cost spiral that follows from that comparison is not the final pressure the architecture faces. Set the money aside for a moment. Set aside the cost figures, the mass calculations, the fuel plants and the power systems, and the redundancy chains. All of that is real, and all of that matters. But there is another dimension to this problem that no budget can fully capture. It is measured not in dollars or kilograms, but in days. And there are a great many of them. Once the crew lands on Mars, they cannot leave whenever they choose. The return to Earth requires the same thing the journey out required. The planets must be in the right positions relative to each other for the transit to work. Earth and Mars align favorably for launch windows roughly every 26 months. Miss the optimal window, and the next one is approximately 26 months after that. There is no shortcut. There is no engine powerful enough to overpower the geometry of two planets orbiting the Sun at different speeds and different distances. Orbital mechanics is indifferent to how the crew feels, how the equipment is holding up, or how badly anyone on Earth wants them home. That means the crew waits. A minimum of roughly 730 days on the surface before they can even attempt to leave. 2 years. Not 2 years in a comfortable research station with resupply flights and evacuation options. 2 years in a habitat the size of a few connected rooms, breathing recycled air, drinking recycled water, eating stored food supplemented by whatever small greenhouse they have managed to grow. Outside only in spacesuits. The Martian sky visible only through windows or a visor. Think about what that sensory environment does to a person over time. No wind on your face, no rain, no smell of grass or soil or open air. Every breath filtered, every sip purified, every step outside requiring 45 minutes of preparation. The landscape does not change in ways a human nervous system was designed to register as refreshing. Mars is rust-colored rock and dust in every direction, strikingly beautiful by any scientific measure. Not the kind of environment human psychology evolved to sustain itself in for 2 years without cost. Research on isolated environments gives us some indication of what to expect. Antarctic winter rover crews, submarine deployments, space station missions, isolation studies deliberately constructed to simulate long-duration missions. The pattern across all of them is consistent. For the first few months, morale holds. Work provides structure, novelty sustains engagement. But around the 6-month mark, something shifts. Small habits that were previously unremarkable become irritating beyond proportion. Irritation becomes conflict. Sleep deteriorates. Concentration falters. Depression becomes common, not rare. The effects do not arrive suddenly. They accumulate gradually, the way fatigue compounds over a run that started at a comfortable pace. By the time you notice them clearly, they have been building for months. On Mars, the mission is not 6 months. It is 24 months of surface time at minimum, plus the transit out and the transit back. Psychological deterioration is not a theoretical risk. It is a forecast. Something else was happening. The psychological pressure, as real as it is, may not be the most serious medical problem the crew faces. Mars gravity is 38% of Earth's. The human body evolved under a full gravity field. Bones and muscles develop and maintain themselves in response to load. Reduce the load, and both begin to atrophy. On the International Space Station, in zero gravity, Astronauts lose roughly 1 to 2% of their bone density every month, despite spending approximately 2 hours each day on exercise equipment specifically designed to slow that process. Mars is not zero gravity. The atrophy rate is slower. But after 2 years on the surface, a crew member would likely have lost somewhere between 20 and 30% of their bone density. That is not a minor reduction. That is the difference between a normal skeleton and one at significantly elevated risk of fracture. Chronic pain, structural compromise in bones that were never designed to fail at that rate. When they finally return to full Earth gravity after years away, their skeletons will be doing so in a compromised state. And that is before anything has gone wrong. Medical emergencies on Mars are a separate category of problem. Consider appendicitis. On Earth, appendicitis is a routine surgical emergency. Diagnosed quickly, treated surgically within hours, survival rate near 100% with proper care. On Mars, appendicitis becomes potentially fatal. There is no hospital, no surgical suite, no anesthesiologist, no blood bank, no radiologist to confirm the diagnosis. A crew of 6 to 8 can include at most 1 or 2 people with significant medical training, usually a physician trained in an emergency medicine, and perhaps 1 additional medic. Complex surgery normally requires a specialized team working in concert. That team does not exist on Mars. What exists is a pressurized habitat, a limited medical kit, the training of 1 or 2 crew members, and whatever they can manage. Telemedicine offers partial relief. Specialists on Earth can advise, guide, recommend, but the communication delay runs to more than 20 minutes one way, 40 minutes or more for a round trip. You cannot have a surgeon talking you through a procedure when their instructions arrive 10 minutes after you needed them. The doctor on Earth is not guiding surgery in real time. They are reviewing a situation report and sending advice that will arrive when the crew member is either stable or already beyond help. Every acute emergency on Mars is handled, in practice, alone. Then there is radiation. Mars has no global magnetic field. It has a thin atmosphere. Both of those would normally provide shielding from the solar wind and from cosmic rays. Without them, the surface of Mars receives roughly 240 millisieverts of radiation per year. Earth's surface, protected by its magnetosphere and thick atmosphere, exposes a person to about 3 millisieverts per year. That is not a slight difference. That is a factor of 80. Over a 2-year surface stay, the cumulative dose climbs well past what NASA currently considers acceptable under its safety standards for any prior crewed mission. Those standards exist because the data is clear. Studies of atomic bomb survivors, radiation therapy patients, nuclear accident workers, and long-duration astronauts all show the same pattern. Dose accumulates. Cancer risk rises with it. The effects may not appear for decades, but they are not theoretical. They are statistical certainties applied to populations, and they become increasingly probable as individual doses climb. Mission planners would be required to make an explicit argument that the scientific and exploratory value of the mission outweighs the elevated cancer risk absorbed by each crew member. Some argue that informed adults have the right to accept that risk. Others argue that no institutional framework can ethically require a person to accept a significantly elevated lifetime cancer risk as a condition of doing their job. That debate has not been resolved. It will have to be resolved before anyone goes. All of this compounds around a core mechanical fact. Every system keeping the crew alive has a finite life. Air recyclers accumulate contaminants. Water purifiers clog with minerals. Spacesuits develop microscopic leaks. The habitat itself, continuously exposed to micrometeorites that Mars's thin atmosphere does not fully burn up, accumulates small punctures. A slow leak is patchable, a fast one is not. Without oxygen, the crew has minutes. Without functional CO2 removal, they have hours to days depending on crew size and available volume. Without water, days. Redundant systems extend those margins. But redundancy is not infinity. 2 backup systems failing simultaneously is a death scenario, and no engineering analysis can reduce that probability to 0. Here is what this picture looks like assembled. Imagine a saw running continuously for 730 days. Each individual tooth is designed to last far beyond a single pass. But you are not running it for a single pass. You are running it for 2 years, and you are watching carefully for the one tooth that finally breaks at the worst possible moment. Every system aboard that habitat is a tooth on that saw. Most will hold. The question is which one fails, and when, and whether it fails in isolation or takes something else with it when it goes. If it goes catastrophically, no rescue is possible. Earth can monitor, Earth can advise, Earth can grieve. A rescue mission, if one were ever sent, would arrive years later. The crew on Mars is alone in a way that no human explorers in history have ever been. Shackleton's men were stranded on ice in a place with no radio contact and no guaranteed rescue, and they were still on the same planet as everyone who might help them. Mars is not the same planet. The crew is beyond reach in a way that is absolute. After 2 years, if all of it is held, the crew boards the ascent vehicle, launches into Martian orbit, transfers to the transit vehicle, and begins another 6 to 9 months of travel home. Total mission duration, roughly 3 years from launch to landing. When they return, they will not step out of the capsule and stand in the sun. They will be carried. Months of physical rehabilitation follow. Weakened bones, readapting to full gravity. Atrophied muscles, rebuilding under loads they have not felt in years. Cardiovascular systems that calibrated themselves for reduced gravity now struggling to manage the full weight of a human body. Lifelong monitoring for radiation-induced cancers that may not declare themselves for another decade or two. The first Mars crew would return to Earth as patients as much as pioneers. And even that outcome, the full mission success outcome, assumes everything has worked. The ISRU plant, the power systems, the life support, the medical kit, the habitat, the ascent vehicle, the transit systems, and the psychology of 6 to 8 human beings living in close confinement under continuous stress for 3 years. All of it, holding together simultaneously without catastrophic failure for the full duration. The cost spiral and the engineering burden are real, but the weight of those 2 years on the surface is its own argument, and it is not the last one. That argument, the weight of the 2 years on the surface, is only one of 2 arguments against a round-trip mission. The second is simpler. It is not about suffering. It is about math. Pull back from all of it for a moment. The ISRU plant, the radiation exposure, the bone atrophy, the psychology of confinement. Pull back from every engineering detail and ask the question that sits underneath all of them. Should humans go to Mars at all? It is not a frivolous question. Rovers like Perseverance and Curiosity have operated on the Martian surface for years. They analyze rocks, drill cores, and search for signs of ancient life. They do not tire. They do not eat or drink. They do not mind the radiation. A failed rover is unfortunate. It is not a tragedy. No one dies. You grieve it briefly, and then you send another. For roughly the cost of one human Mars mission, you could send approximately 10 robotic missions, 10 separate spacecraft, 10 separate sets of instruments, 10 chances to find something significant. A failed robot costs money and time. A failed crew costs something that cannot be replaced. Humans do have advantages that robots cannot match. A human geologist standing on Martian soil can look at a rock formation, notice something unexpected, and make an immediate decision to investigate. A robot needs instructions sent from Earth. By the time those instructions arrive, the moment may have passed. Conditions change, light shifts. Humans adapt in real time in ways that current robotics cannot replicate. A human crew can also perform complex repairs, think laterally under pressure, and improvise in situations no engineer anticipated from 60 million miles away. But here is the question that will not go away. Are those advantages worth hundreds of billions of dollars and a significant probability of crew death? There are 2 honest camps on this. The first says yes, and the argument is not primarily scientific. It is something older. We climb mountains because they are there. We sailed to Antarctica not because the data return justified the cost, but because something in human nature insists on presence, on crossing thresholds, on standing somewhere no one has stood before. Not going to Mars feels To people in this camp, like giving up on something essential about what we are. The second camp is equally serious. Space budgets are limited. Every dollar spent landing a human crew on Mars is a dollar not spent on robotic missions to the moons of Jupiter and Saturn, to the asteroid belt, to the telescopes that might detect signs of life around distant stars. Scientific return per dollar is higher for robots. Risking lives and spending vast sums to plant a flag is romanticism dressed as policy. Both camps have legitimate claims. Neither one can be settled by data alone. But if the answer is yes, if you decide that humans should go, then you inherit every cost described in the preceding hours. The ISRU plant, the power system, the radiation exposure, the 2-year wait on the surface, the ascent vehicle, the return cruise, the rehabilitation, the medical monitoring for decades afterward. You inherit all of it. And at some point, staring at that inheritance, a different question surfaces. What if they simply did not come back? A one-way mission changes the entire equation. No ascent vehicle, no ISRU fuel plant producing return propellant, no 2-year wait on the surface for a departure window to open, no 6 to 9 month return cruise to provision for. The mission becomes simpler. In some ways, it becomes cheaper. In some ways, it becomes safer, because the systems you eliminate are also the systems most likely to strand or kill a crew trying to leave. But one way is not just a technical change, it is a fundamental shift in what you are asking people to do. You're asking them to leave Earth forever, to walk onto a spacecraft knowing they will never walk on a beach again, never swim in an ocean, never hike through a forest or stand in the rain, never smell a forest after rain, never attend a family gathering, never visit the city they grew up in. Every goodbye they make before departure is final. Every last look at Earth from the spacecraft window is really the last. No changing their minds. No coming home if something breaks. No coming home if someone they love becomes ill. No coming home at all. The idea is not new. In 2012, a Dutch entrepreneur named Bas Lansdorp founded a private organization called Mars One. The plan was straightforward. Send volunteers on a one-way trip. Establish a permanent colony on Mars. Resupply periodically from Earth. Never bring anyone back. Fund the whole operation as a reality television event, broadcasting the selection, the training, the journey and the landing as global entertainment, using the advertising revenue to pay for subsequent missions. Mars One received more than 200,000 applications from people in over 140 countries. Not 200 applications, not 2,000, 200,000. They were teachers, engineers, students, military veterans, doctors, artists. Some held PhDs, others had no relevant qualifications but were willing to learn whatever was required. What they shared was a single willingness: to leave everything behind for a chance to be part of something that had never happened before. Mars One failed. Financial problems mounted faster than funding materialized. The technical challenges proved far deeper than the organization had anticipated or planned for. By 2019, Mars One had declared bankruptcy, having built no hardware, signed no launch contracts, and developed none of the enabling technology a real mission would require. The mission never came close to leaving the ground, but 200,000 applications said something important about human nature that no bankruptcy can erase. This was not the first time. In 1620, the Mayflower Pilgrims who sailed for the American continent knew, realistically, that they were unlikely to return to England. The voyage itself was dangerous. The mortality among early settlers was horrific. They came anyway, drawn by religious freedom, economic opportunity, or simply the pull of a fresh start somewhere new. The people who made that crossing understood, on some level, that they were leaving for good. 2 centuries later, Oregon Trail pioneers undertook months-long journeys across hostile terrain, leaving behind everything familiar, knowing that many of them would not survive the crossing. Many did not. In 1914, the explorer Ernest Shackleton placed an advertisement for his Antarctic expedition. The wording was plain: men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success, He received more than 5,000 applications for 28 positions. The pattern is not complicated. People accept extreme risk, including permanent departure from everything they know, for a chance at meaningful participation in something historic. They have done it across centuries, across cultures, across every variation of circumstance. The Mayflower did not attract the timid. The Oregon Trail did not fill with people who needed a guarantee. Shackleton did not need to search for volunteers. They came to him. The bottleneck for a one-way Mars mission is not finding people willing to go. It never was. The bottleneck is the technology that does not yet exist at the required reliability. The money that no government or private organization has yet committed at the required scale. And the political will to look at the full cost, the full risk, the full irreversibility of asking people to leave Earth permanently, and decide that the answer is still yes. Those three things are harder to solve than the volunteer problem. And they are the reason a human being has not yet set foot on Martian soil. So the question shifts. Not whether people will go, they will. The question becomes, which people exactly, and what does it take to make them ready? The selection process would be unlike anything that exists today. Technical skill matters, but it is not the primary filter. Plenty of people can learn to pilot a rover or calibrate a spectrometer. The deeper question is psychological. Can this person function when frightened? Can they perform a complex task at the edge of exhaustion, in a suit that is keeping them alive, on a world that does not care whether they succeed? Can they sit across a dinner table from the same 5 people for the 500th consecutive night and still resolve a disagreement without letting it become a wound? Those questions are harder to answer from a resume. Psychological screening would be rigorous in ways that have no civilian equivalent. Assessors would look for emotional stability, stress resilience, and the specific ability to manage interpersonal conflict constructively rather than letting it accumulate. They would also be screening out candidates with histories of depression, anxiety disorders, or mental health vulnerabilities that could become debilitating under sustained pressure would not make the cut. Not because those conditions are weaknesses in ordinary life, but because on Mars, a psychological crisis is also a survival crisis. There is no institution to absorb the disruption. There is no one else to cover. The group dynamics problem is just as important as the individual assessment. 4 to 6 people living together for years must be compatible in ways that go well beyond professional respect. Research from Antarctic winter rover stations, submarine deployments, and long-duration ISS missions all points the same finding. Interpersonal conflict is consistently one of the greatest threats to crew performance in isolated environments. Not equipment failure, not boredom, the people. And the thing that generates the conflict is rarely dramatic. It is almost never dramatic. It is the small things. Someone who leaves food out in the shared kitchen. Someone whose sleep schedule keeps shifting and disturbs the person in the bunk next door. Someone whose humor lands badly 300 days in a row. Irritants that would dissolve in normal life, where distance is available, become unbearable when escape is impossible. One toxic personality can compromise the entire mission. Not slowly, quickly. This is why some planners argue that crew compatibility may matter more than individual excellence. A slightly less technically brilliant team that functions well together will outperform a collection of brilliant individuals who grate on each other. The crew needs shared purpose too, something that binds them when circumstances push against cohesion. Historically, that binding force was often religion or ideology. Modern candidates might not be religious, but they would need something equivalent. A deep, genuine commitment to the mission itself. Not excitement about the adventure, which fades. Commitment to the meaning of what they are doing, which does not. Training would take 5 to 10 years, depending on the candidate's starting point. That is not an estimate. It is an acknowledgement of what these people would need to be capable of. Not competent in. Actually capable of. Under pressure, in the dark, with no one to call. Every member of the crew would need medical training thorough enough to handle emergencies from broken bones through surgery. Every member would need enough engineering knowledge to diagnose and repair any system in the habitat. They would need to understand Martian agriculture, geology, rover operations, drone piloting, and construction with local materials. A crew member who masters 3 of those things and relies on others for the rest is a liability in a crew of 6. Everyone has to be able to do almost everything. Training would happen in Mars analog environments on Earth, the Mars Desert Research Station in Utah, the Flashline Mars Arctic Research Station in the Canadian Arctic, volcanic regions in Iceland, high-altitude deserts in Chile, months at a time in simulated habitats, with simulated equipment failures, with communication routed through an artificial delay to mimic the real thing. The goal is not to simulate Mars perfectly. That is impossible. No Earth location replicates thin atmosphere and low gravity and extreme cold and elevated radiation all at once. The goal is to train the decision-making process under pressure, and to find out before departure which dynamics in the crew are dangerous. But the reality was different. Even 10 years of the most rigorous preparation cannot fully answer the most important question. Training prepares technical skill. It cannot guarantee what happens to the human mind when novelty fades. The habitat would be pre-positioned, landed months or years before the crew, tested, verified. Automated systems would deploy solar panels, establish airlocks, confirm that life support is functioning. The crew would land nearby, close enough to reach the habitat on foot in a spacesuit within an hour or 2. The first weeks would be dominated by work. Unloading equipment, moving in, testing every system, establishing routines. Everything would be new. The crew would be making history with every breath. That phase ends. After a few months, the reality of the situation sets in. This is not an adventure with a return date. This is life now. Same habitat, same rooms, same faces, same food, same routine. The Martian landscape does not change the way Earth landscapes change. There is no weather in the dramatic sense. No rain, no clouds forming and breaking apart. The butterscotch pink sky looks the same today as it did yesterday, and will look the same tomorrow. The small pale sun crosses overhead, a little dimmer and more distant than the one they grew up under. The rust-coloured rocks sit exactly where they were. Seasons exist, but only as gradual temperature shifts, not as visible transformation. Mars is geologically patient in a way that the human mind was not built to absorb. Work fills the days. Geology, sample collection, the ongoing search for signs of ancient microbial life, Martian meteorology, technology testing for the colonists who might follow, data exchanged with Earth scientists, compressed into packets, transmitted across the delay. The work is meaningful, but meaningful work inside a sealed environment, with the same 5 people, is still a closed world. Agriculture becomes one of the anchors of daily life. Pressurized greenhouses, heated and lit by LEDs, calibrate for photosynthesis, would grow the crops that supplement and eventually replace the freeze-dried stores from Earth. Lettuce and spinach, and radishes for quick nutrition. Tomatoes, potatoes, calorie-dense enough to grow in poor soil, a practical staple. Possibly rice or wheat if space allowed, though those require longer cycles and lower yields per square meter. The soil beneath those crops is not simple. Martian regolith contains perchlorates, a class of toxic compounds that interfere with thyroid function. Processing the regolith to remove them, then supplementing the result with organic matter composted from human waste, is not glamorous work. It is essential work. Water comes from melted subsurface ice, purified through the same recycling systems that handle the crew's drinking water. A crop failure would not be a setback. It would be a crisis. A seal failure in the greenhouse, a disease spreading through the plants, a lighting malfunction sustained for long enough to kill a harvest. The emergency freeze-dried rations exist, but they are finite. They do not replenish themselves. Maintenance runs parallel to everything else, always. Spacesuit seals degrade, air recyclers clog, mineral deposits build up in water purifiers. Martian dust accumulates on solar panels despite every protective measure. Batteries lose capacity over time. The workshop is never empty. Spare parts get used, and the inventory of replacements slowly thins. Raw materials for fabricating new components become precious. This is the part of Mars that the popular imagination tends to skip over. Not the grand geology or the search for life, but the constant, unglamorous work of keeping the machinery from dying. This is also exactly where a human crew provides something no robotic mission can. A human engineer can walk up to a broken pump, observe how it failed, understand the failure mode in context, and improvise a workaround with what is available. The Apollo 13 crew did precisely this. They built a CO2 scrubber from duct tape and plastic bags in 4 hours because their lives depended on it, and they had no other option. That capacity to understand and improvise is what saved them. Mars colonists would need that same capacity sustained not across 4 days, but across years. Not a single emergency resolved with brilliance and then over, but an ongoing relationship with fragile systems that require continuous creative problem solving. The social structure would be organic. In a crew of 6, there is no room for rigid hierarchy in daily life. Everyone contributes. Everyone's judgment matters. A mission commander holds authority in genuine emergencies, but most decisions happen through consensus, which requires a kind of social skill that no amount of rover training provides. Rituals and celebrations become structurally important. Birthdays, anniversaries of the landing, first harvest, holidays drawn from the various Earth cultures represented in the crew. Over time, new Martian traditions, specific to this place and this group, and this peculiar moment in history. Conflict is not a failure state. It is an expected condition that must be managed rather than suppressed. Disagreements about task priority, fair allocation of work, resource decisions, the tension between scientific goals and survival priorities, small resentments that fester when there is nowhere else to go. The crew would need conflict resolution skills practiced to the point of reflex. Address issues early, before they crystallize. Express frustration without personal attack. Forgive minor infractions because the alternative is accumulating a ledger of grievances in a space the size of a suburban house, indefinitely. Regular group meetings to air problems before they become crises, not optional. Psychological support continuing after landing through counseling and group therapy. Telecounseling with Earth therapists, routed through the communication delay as message exchanges. Not real-time sessions. The therapist's response arrives 20 minutes after the question was sent, which means the conversation happens in asynchronous fragments, not dialogue. It is something. It is not enough on its own. Romantic relationships will form. In a crew of 4 to 6 people living in close proximity for years, they are close to inevitable. Some planners have suggested sending established couples, on the theory that stable relationships provide psychological support. Others point out that relationships often do not survive the specific pressures of a Mars mission, and a painful breakup in a habitat the size of a small apartment could be catastrophic for the whole crew. There is no clean answer. It is one of the genuinely unresolved questions in mission planning, and anyone who claims otherwise is not being honest about what we do not yet know. Pregnancy in the first missions would be a disaster, and the word is chosen carefully. There would be no obstetrician, no pediatrician, no neonatal care of any kind. The effects of low gravity and elevated radiation on fetal development are not known. They have never been studied in humans because humans have never been in that environment for the relevant duration. An infant in a pressurized habitat would stretch the crew's resources and attention beyond what a survival mission could absorb. Children come later, after the colony is larger and more stable. In the first years, they cannot come at all. What the first crew would be doing, in every practical sense, is learning what it actually means to live on Mars. Not visit it, not explore it on a timetable. Live on it with the full weight of permanence. And what they learn will determine what everyone who comes after them has to carry. Time passes. That is the quiet truth behind everything that follows. The first crew learns what it means to live on Mars. They pass that knowledge to the crews that come after them. The colony grows, slowly at first, then less slowly. And then, one day, a child is born there. Not on Earth, not during a mission. On Mars, in a pressurized habitat, under a butterscotch sky, on a world that has never known rain. That child will open its eyes and Mars will simply be home. Think about what that means for a moment. Children born on Mars will grow up learning Earth the way people on Earth might learn about a distant country they have never visited. Through images, through stories, through the accounts of parents and grandparents who made a crossing that will by then feel mythological. Earth will be real to them in an intellectual sense. They will know about oceans and forests and billions of people living under an open sky. But it will be abstract knowledge, the kind of knowledge you hold in your mind without ever feeling it in your body. Mars will be what they feel in their bodies, the rust-colored dirt visible through every viewport, the thin, cold air that would kill them in seconds without a suit, the daily rhythms of a pressurized life, the hum of recyclers, the weight of routine that keeps the habitat alive. Mars will be ordinary to them. It will be the only ordinary they have ever known. The answer was stranger than expected. Those children may never be able to visit Earth. Not because they are forbidden. Because their bodies, grown in 38% of Earth's gravity, will have developed differently. Bones calibrate themselves to the loads they carry. Muscles build to the forces they regularly resist. A child raised on Mars will be adapted to Mars, and adaptation is not a reversible process. Earth's gravity, roughly 2.5 times what they have always known, would feel like being crushed. They would not merely feel heavy. They would struggle to stand. Their hearts, built to pump blood across a Mars-sized gravitational field, would strain against demands they were never shaped to meet. Earth, the planet where their species evolved over millions of years, would be physiologically dangerous for them. They would be Martians, not as a label, not as a cultural identity, in the full biological sense, adapted to their world, unable to survive on the planet their grandparents came from. And they would not find this sad. They would not grieve Earth. You cannot grieve a place you have never experienced as real. Earth would be the alien world. Mars would be normal. They would learn Martian geography, Martian geology, the story of the first crews who came from Earth and stayed, the early struggles, the first harvests, the first deaths, the slow expansion as more missions arrived and the colony thickened from a foothold into something with depth. They would learn that their own existence is possible only because those first people accepted a one-way ticket and never asked for it to be otherwise. As the colony grows, the question of governance becomes unavoidable. In the early years, authority comes from wherever the funding came from. A space agency, a private consortium, a coalition of nations. The first crew follows mission rules, but rules written on Earth for a mission that is still largely theoretical do not survive contact with the lived reality of Mars. The colony will eventually need to govern itself. Who decides how resources are allocated? Who resolves disputes? Who has rights? Who owes obligations to whom? History is not encouraging that this process goes smoothly. The American colonies began as extensions of British authority and ended by declaring themselves something else entirely. Australia began as a penal colony and became a nation. These transitions did not happen quickly or painlessly, but they happened because the physical separation between a colony and its founding power eventually makes the founding power's authority theoretical. You cannot enforce orders that take 40 minutes to arrive. You cannot project military force across hundreds of millions of kilometers against a colony that controls its own life support and has nowhere left to retreat. Mars has a structural advantage that no colony in Earth's history ever had. Every command from Earth arrives at least 20 minutes after it was sent. By the time Earth knows Mars's response to an order, another 20 minutes have passed. Earth can state a policy. Mars can implement whatever it decides before Earth even receives the reply. Political independence is not just likely for a mature Mars colony. It is written into the geometry of the solar system. What does Earth actually get from Mars then, once the colony is no longer dependent on Earth for survival? This is a question worth sitting with, because the answer is not the obvious one. Mars has resources, water ice in abundance, iron oxide across most of its surface, potentially rare Earth elements in its crust, deuterium in its atmosphere, which becomes interesting if fusion power ever matures into a real energy source. But extracting those resources and shipping them to Earth requires enormous infrastructure and energy. The Moon is closer. The asteroid belt is richer. Almost anything Mars can offer in raw materials can be obtained more cheaply from somewhere else. What Mars offers Earth is something that does not appear on a balance sheet, a second location. For 3.8 billion years, every living thing that has ever existed on Earth lived only here. Every organism, every ecosystem, every experiment that evolution has run across the entire history of complex life. All of it concentrated on a single world, dependent on a single biosphere, vulnerable to whatever this one planet encounters. That is an extraordinary concentration of everything that matters. And Earth is not safe. It has never been safe. 66 million years ago, an asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula. The energy released was equivalent to billions of nuclear weapons detonating simultaneously. Dust and debris filled the atmosphere. Sunlight dimmed. Photosynthesis collapsed. Food chains collapsed. The dinosaurs, which had ruled terrestrial ecosystems for 160 million years, were gone within a geological instant. Roughly 75% of all species went extinct. That was not the worst one. 252 million years ago, an event now called the Permian-Triassic extinction killed approximately 96% of all marine species and 70% of terrestrial vertebrate species. The cause is still debated. Unprecedented volcanic activity, possibly combined with other factors. Whatever happened, Earth's biosphere came close to complete sterilization. Life recovered. But recovery took tens of millions of years, and civilization is 10,000 years old. Anatomically modern humans have existed for perhaps 300,000 years. Civilization, with cities and writing and organized agriculture, for roughly 10,000. We are newcomers on a 4.5 billion year old planet, and we arrived recently enough that the next extinction level event is not a historical abstraction. It is an actuarial fact. These events happen. They will happen again. The question is whether there is anyone somewhere else when they do. A Mars colony changes that calculation, not by making Earth safe. Nothing makes Earth safe, but by creating a second location for human civilization. A backup. If Earth is devastated, Mars continues. The knowledge survives. The lineage survives. The accumulated 10,000 years of what humans have learned and built and thought and imagined survives in compressed form, in a colony that did not need to be large to matter, only real. This is not cowardice. It is not giving up on Earth. It is the recognition that the best way to protect something irreplaceable is to not keep all of it in one place. The colony scaling matters here. 4 to 6 people is a foothold. It can be destroyed by a single equipment failure or a single bad winter. 40 people has redundancy, enough that individuals can be lost without the whole collapsing. 400 has genuine specialization, engineers and doctors and farmers who are not all trying to do everything simultaneously. 4,000 has culture, economy, political structure, a self-sustaining social fabric. Each step requires the one before it, and the one before it required people willing to be first. The first colonists spend their working lives building toward that sequence. They arrive in their 40s or 50s. They have perhaps 20 or 30 years of useful work ahead of them on a planet that ages bodies faster than Earth does. Radiation accumulates. Low gravity takes its quiet toll. They will reach the end of their lives in their 70s or 80s in a colony that is larger than when they arrived, but still small by any earthly measure. They will be surrounded by people who know their names, who owe their presence there partly to what these founders chose and did not choose. They will die on Mars. There is nowhere else for them to die. Burial in frozen ground is hard, and the resources for elaborate ceremony do not exist. Their bodies will be placed in a designated area outside the habitat, covered with rocks, marked with whatever simple monuments the community can make. The first Martian cemetery. The founders, permanently part of the planet they spent their lives trying to make livable. Future colonists will visit that cemetery, Children will learn the names carved on those rocks. They will understand, in the way that people understand things that are simply part of the world they were born into, that their lives exist because someone made a choice decades or centuries earlier and never reversed it. The first colonists will be mythologized. Their failures will be smoothed over. Their human flaws will fade. What will remain is the shape of what they did. They came. They stayed. They built something that outlasted them. Origin stories do not have to be perfectly accurate to be meaningful. They have to be true in the ways that matter. The first humans on Mars will never come back. Not because they failed. Not because they were trapped. Because coming back was never the plan. The plan was to stay, to build, to prove that humans can live on another world, to take the first step towards spreading what we are and what we know and what we have imagined across more than one fragile rock, orbiting one ordinary star. That step, and the choice it required, and the lives it cost, and the lives it made possible, is what the mission will ultimately mean. Not the landing, not the flags, not the science, though the science will matter. The meaning is the staying, and what comes after.